session of the robotics seminar. I'm very happy to introduce you to Emily Cross today. So Emily is a professor of cognitive and social neuroscience at ETH Zurich in Switzerland, where she leads the social brain science lab. She and her team study the social perceptions and interactions between humans and artificial agents, and how aesthetics shapes our interactions with other humans and AI. So after Emily completed her PhD in cognitive neuroscience at Barton College, she did a postdoc at the Max Planck Institute in Germany. But what's really amazing is that Emily has had faculty positions at least 5 different universities. So besides ETH, Emily was at the University of Glasgow and Macquarie and Western Sydney universities, just to name a few. So while Emily and her lab moved quite often, it's immensely impressive how the research is so cohesive on the study of cognitive and neuroscience of human-agent interactions. Emily has received several awards, such as an ERC grant on social robotics, and she plays a major role in thinking about ethics and AI, serving as a member of UNESCO's International Bioethics Committee. Besides this, Emily is also a dancer. And I think this really shows how interesting it is that our things outside academia can really influence our academic journey. So Emily comes actually straight from a drive from Ohio to be here with us. So let's just clap our hands. Welcome, Emily.
Thank you. Thank you so much, Patrizia. And I'm going to treasure forever the fact that I've been introduced by a new mother with a tiny and adorable little baby too, because that is amazing. And I'm very happy to be here. I've never actually been to University of Michigan before, and because I come from a family who's gone to Ohio State University. This is a bit controversial that I'm here right now, but so far, nothing bad has happened, and it is just such a pleasure to be here. So the advertised title of my talk was this: Social Robotics is not just about machines, it's about people, psychology's role in developing social machines. And I'm going to talk about that, but I'm going to give you a slightly different title. So we're going to cross that one out, and we're going to talk about something that comes from kind of that same paper that has this title, but is a little more focused, because I'm speaking to one of the world's preeminent robotics groups, departments, collections here at Michigan. And I want to talk about something that's really near and dear to my heart that, again, comes from this paper, but it's much more focused on the physical embodiment of robots. And not just the physical embodiment of robots, because I know there's a lot of expertise in this room, and a lot of you are doing incredibly cool stuff with physical robots. But what's required to have physically embodied robots that are socially engaging? And this is where my interest and expertise in social robotics comes in. So my new title is When Minds Meet Matter, the Stubborn Physics of Embodied, and that should probably say Embodied Social Intelligence. So that's what I'll be talking about. And Patrizia gave a very lovely, thank you, introduction, but just to give you a little visual schematic of kind of where my research kind of comes together, because aesthetics were mentioned. We do a lot of stuff with social connection between two humans or multiple humans, and also between humans and artificial agents. So my team is really working across these three main areas of embodied algorithms, so social robotics, embodied interaction, so what's going on when you're engaging with other humans, what's going on in the brain, what's going on in your behavior, what's going on in your biological, physiological signals, such as heart rate, skin response, and these things. And then also embodied creativity. So we're really interested in how we use our bodies to make art and to appreciate art. So all of these can kind of fall under the umbrella of embodied intelligence, and that's what my team is really working on and towards right now. So talking a bit more about where we are with the embodiment of social artificial agents, I'd like to begin with what can be, for many in the robotics industry, the social robotics industry, an uncomfortable truth. And that is the fact that if we look at this slide here, we can see many very well-known and well-loved social robots, ranging from Jibo, Cosmo, Moxie, Now, and Pepper. These are all robots, except for Jibo, that we've had and used in our lab, and we love them a lot. And not just, the odd social robotics researchers, many robotics researchers, and also airports, shops, parents, such as for the two toy robots there, Cosmo and Moxie. many members of the public have engaged with these robots. And together, these 5 platforms have had over $500 million in funding that they've attracted as they kind of were launching. But as you'll also know, each of these companies has now folded or has been bought by another company and is still are still experiencing financial troubles. And this is interesting because each of these robots has what kind of looks to be an engaging embodiment that should be engaging people on a social level, yet each has failed to sustain long-term engagement. So one of the questions I want to ask is, we've sent all of these robots on to robot heaven. I mean, again, some of us are still working with them. We still have quite a few of these robots in my lab, and we're still trying to work with them. But commercially, they're kind of not around anymore. So a question I want to ask is, what if the problem with these robots wasn't so much in their programming and what they were doing and how they were engaging with people, but more about their embodiment and either how they were manifest in an embodied form or how their behaviors and their embodiment interacted? What if the failure was happening there? So this brings us to a central paradox. And this paradox is when bodies make promises that they just can't keep. So physical embodiment really should be social robotics' greatest advantage over disembodied and screen-based generative AI. However, we can see all of these things here, and we know that there are millions of people who use these technologies every day and often for very social means. And having a body should, in theory, make technologies even more socially engaging. But the problem is, and we have many videos, you can look up many compilations of robot fails, but these are, especially that middle one there, it's a really simple social task to give someone a high five, and that is a real big challenge for many of these types of robots. So instead of being the killer app, having a body, a social agent embodied in kind of something that can interact with humans in the same physical space, embodiment has really become AI's biggest liability, and it continues to be. So a question I want to ask is, why is the physical embodiment of artificial intelligence in social contexts so challenging, and what might it take to get this right? So in this talk, I'm going to go through 5 major challenges. Some will be more familiar, some might be less familiar. I'm not going to spend the same amount of time on all 5 challenges. I will try to bring in some of the work that my team has done to highlight not necessarily solutions per se, but just where these challenges are arising and why they're important and how we might think about overcoming them. So the first one kind of speaks to what I just already mentioned, and this concerns what bodies promise but fail to deliver. So when we talk about this, we could talk about the assumption trap. So if you walk into a room and you see an Amazon dot sitting on the table, you can walk up to it and say, Alexa, play the song that won the Eurovision Song Contest last year, and you'll have your expectations met. The Alexa will be able to do that, and the song will play. If you walk into that same room and you see a now robot sitting on the table, and many of you will know this, and if you were a lay person who doesn't have an experience in robotics engineering in programming, you might think it's quite sensible to say, now hand me that book. And because now is sat there, embodied and situated in the same context as you're walking into and that you see, and now has what looks to be a head with what looks to be eyes on it, and it has hands, it has bodies, a torso, you'd expect that this could be a trivial task. But of course, I know, and many of you will know as well, that now it takes a lot of programming, and now probably even with the best programming possible, we'll still not be able to pick up that book because of the actuators in the hand. It's not really designed to do that. So we have a body that looks humanoid and looks like it should be able to do the things, on a smaller scale that we do with our bodies, but it couldn't be farther from the truth. So the problem is that the physical presence that the robot brings with it really implies perceptual access and intentional action. And when the body is humanoid, that's even more so the case. So the problem is that bodies are creating expectations that current AI cannot fulfill. If we look at this spectrum of many social robotics agents that have been developed and released over the years, there's been this idea that, kind of moving away from Cosmo and Jibo and more towards, Ishiguro's Geminoid robots, the iCub, Pepper, and Naval, all these other robots as well, that the more humanoid you make a robot look like, to kind of give it, give it a torso, give it a face, give it, facial expressions, the more easy social interactions will be. And if you want robots to do things in a socially collaborative manner with people, you better make your robot more humanoid looking. this is an idea that's been around for a long time, and it chimes well with another idea, that kind of hypothesis that comes from developmental psychology, which is the like me hypothesis. Sometimes people know this as the homophily hypothesis, but this hypothesis essentially stipulates that we are biologically hardwired to engage with self-similar agents. So babies, from the moment they're born, kind of orient more towards voices, towards languages that look like what they were hearing in the womb, and children, kind of seek out and play with and are more likely to socially affiliate with other children or adults who look like them, speak like them, move like them. So this like me hypothesis, we have lots of evidence from developmental biology, from developmental psychology, and if you look at the robotics development space as well, you'll see that this is very much happening there. And that's great in a way, except that it's not entirely based on, well, it's based on fact, but we don't need to have agents that look like humans in order to have people engage with them in a social way. And what do I mean by this? Well, hopefully this will play. Yeah. We can think of many of the brilliant creations from Pixar, such as, not Pixar, but also the film industry more generally, where we have artificial agents that don't look a thing like humans, that do not have at all any like-me features, but are incredibly socially engaging. From R2-D2 to WALL-E to even the Pixar bouncing lamp, we have many options. But we also have a really interesting study that came out many years ago from two psychologists called Heider and Simmel. And some of you might have seen these animations before, but they were very simple animations that were made with the researchers having kind of some cutout magnet shapes underneath a magnetic table, and they used other magnets to animate these shapes in very simple ways. But as you will hopefully be seeing as this story unfolds, people are able to infer really complex social states, that one of these shapes is bullying the other two, that the shapes are afraid, that the shapes are trying to help each other. So really quite sophisticated social attributions from two-dimensional shapes that are animated with magnets. So we do not need human bodies to try to understand, teamwork, collaboration, anger, all the things that are going on in this little animation right here. So what this means is that our brains really do encounter very little challenge with attributing socialness to very basic things. So we do not need human bodies. We do not need human faces to see not just socialness, but really quite sophisticated emotional behavior in artificial agents. So we've looked at this a little bit ourselves, and in a brain imaging experiment that was a combination of brain imaging and behavioral experiment. And we did this with people. We asked people to play a series of rock, paper, scissors games with a bunch of different agents while we were scanning their brains in an MRI scanner. So essentially, what we did is we introduced participants to 4 different opponents that they were going to be playing rock, paper, scissors against. So we showed them they're going to be playing against a computer algorithm, and this was just represented by seeing a screensaver. And we said, this is just kind of algorithmically deciding which rock, paper, scissors to choose on each gameplay. We also told them that they were going to be playing against the Cosmo robot, and they got to meet this robot in person and see it do its kind of, who here has seen the Cosmo robot before? Okay, so not everyone, but some people have. So it's very, very cute, it's very sociable, and it doesn't speak, but it doesn't have an animated face, but it does have animated eyes, and it kind of can scoot around and do funny little behaviors. We also told them that they'd be playing against the Pepper robot, which is very humanoid, very kind of familiar human-like face there, and a human experimenter. So these were they got to meet all 4 of these agents kind of in person and before they went into the brain scanner. And then we said there's going to be like a live video feed, and you'll get to see how each of these agents responds when it wins or loses against you. We did tell them that the 2 robots were being kind of fueled by artificial intelligence, but we didn't really go much beyond that. And what we found really interesting is after people played all these game rounds against these 4 different agents, we also asked them a bunch of things about what they felt when they played against these 4 different agents. And, were any agents more interesting or more challenging or more kind of social to play against than the others? And we found a really interesting thing here. And I won't go into great depth of the neuroimaging results, because this is probably a crowd who's not as interested in the brain science pieces. But we were able to kind of focus in on brain regions which we know from the last 20 years of social neuroscience research are really highly implicated in thinking about others' minds. So we talk about brain regions that are involved in mentalizing and kind of taking the intentional stance and trying to understand what others might be thinking about us, and when we're trying to think about what others might do next. So we kind of focus in on these mentalizing regions. So these include kind of parts of the temporal junction, which is right here, and the medial prefrontal cortex, which is kind of more around there. And what we find is we can model our data in a few different ways. And we see that the human brain regions that are implicated in thinking about others' minds are more robustly engaged by social behaviors than by social looks. And what do I mean by that? I mean that our participants in all of these kind of post-experiment questionnaires told us that they found the Cosmo robot to actually be a lot more social and sociable than the Pepper robot, because when Cosmo won, Cosmo would do a kind of a happy little animation and kind of spin around and put his fork up and down. And when Cosmo lost, have a little temper tantrum, whereas, Pepper just has this kind of very static face. And when Pepper won, Pepper would kind of, do this. And when Pepper lost, Pepper would go like this. So much more kind of robotic, much more rigid in some ways. And people found that Cosmo is this little mechanoid robot that can sit on the palm of your hand. They found these animations to be much more social. So it's really quite interesting that we're seeing parts of the brain that are hugely implicated in social cognition and social perspective taking coming much more online when we see an artificial agent that has social behavior. The social appearance, it matters, but it doesn't matter as much as behavior. So this is kind of, I think, an interesting place or point where human neuroscience can give us interesting insights that we can't just get from how people behave, and we can't just get from people's kind of questionnaire reports alone. So a really kind of interesting point there. And this can lead us to the question of, it's not, do we need human-like bodies, but which specific features of embodiment might be driving social engagement? So that's the first challenge. Now we can move to the second challenge, which is kind of a variation on a theme. And this is the generative AI mismatch. So what I mean here, and this is one that's becoming much more interesting as Gen AI's kind of powers and sophistication continues to improve. What we're seeing here is we now have many robots, including this naval robot. We have one of these in my lab. And you can see this with Now or Pepper, or many of the humanoids as well that have speech capabilities, that the language capabilities of these robots is skyrocketing now that they're imbued with generative AI abilities. So you can walk up to the naval robot and say, explain quantum physics to me, and this robot will have no problem doing that. And we're seeing all of a sudden, like this has been a big problem with social robotics research for a long time, that language hasn't been so great, but LLMs really is starting to make language quite sophisticated with these robots. But then kind of coming back to this, situated embodiment thing that I mentioned in one of the previous slides, it makes the problem that robots have really sophisticated verbal abilities, but really basic physical abilities even more pronounced. So it's kind of widening this gap in an even more remarkable way. So bodies are not only not able to match conversational capabilities, but that gap becomes bigger as conversational capabilities really take off. So people become confused. Okay, this robot can, discuss very sophisticated things, but it really can't do basic tasks like picking up my keys. And this expectation gap continues to grow. And this is just something that I feel like social robotics developers need to be mindful of. And it's something that, once you lose a user's trust in this way, like that this robot, okay, it's a really sophisticated, voice agent, but it really doesn't really do much with its body, it's really hard to get users back on board. So one interesting kind of counterexample, or not caveat, but just a case that kind of proves this point is the Paro robot. And many of you will be familiar with this robot as well. And this one really proves the rule, because Paro is a very simple robot in many ways. It's like a big cuddly baby harp seal. And it's been really successful in the kind of limited application domains it's been put into, such as a kind of emotional support robot, especially for those in aged care homes and those with dementia. It's, researchers report that it's really quite comforting that people can stroke it and it will kind of open and close its eyes, move its head, and coo a bit. And I'd like to propose that this robot succeeds precisely because people's expectations match its really limited abilities. I just heard from one of my colleagues who's done a lot of work with the Paro that the company that makes Paro has been approached multiple times to have speech capabilities brought into this platform, and they adamantly refuse because they think that that will ruin what that robot is and what it does. And you can see that being the case. And I'd really support that, that thought of theirs, because I think, again, once Paro can start talking, it becomes a very different robot, and not the same one that's able to provide this sort of comfort and this suite of behaviors that really matches what its body looks like. All right, moving to the third challenge. This is one that might not be such a big problem for other types of embodied robotics testing and research and development, but I think for social robotics, this one is a pretty big challenge. And this is the autonomy illusion. And what I mean here, I'm talking about the Wizard of Oz technique. And of course, the Wizard of Oz technique is spectacularly useful when you're developing new robotic behaviors. There was a book chapter by Tony Belpame that came out about 5 years ago, which was titled Advice to Young Social Robotics Investigators or Students who are trying to kind of come up in this field. And he talks about a lot of the state of the art of the field, a lot of the challenges, and kind of a bit of future forecasting about where we might be going. But in this chapter, he reports a rather well-researched estimate that over half of published human-robot interaction studies till 2020 used human operators to some extent. Sometimes those were light touch human operators doing just a little bit of Wizard of Oz, and sometimes it was full Wizard of Oz. And this is a really interesting problem because, of course, again, it sets expectations for what these agents might be able to do autonomously really high, and they just can't deliver. So many of you might also be familiar with this video that came from the Tesla AI event back in 2021, which is just so special on so many levels. But we see this video of this agent, which, you know, Elon Musk makes no bones about, and says, oh, yeah, obviously that's a human. But he says, and this is a direct quote from this launch event, that we'll have a prototype sometime next year that basically looks like this. Spoiler alert, Tesla does not have a prototype that basically, look, I mean, it looks like that, but it cannot move like that. And it does not have the physical intelligence to move like anywhere close to what you see this person in a robot suit doing. So, you know, I know it's not Wizard of Oz per se, but it's setting expectations with kind of human involvement, and human in the loop, human is the loop here, that really kind of, when investors get involved, when others get involved, it's just really something that these companies and these agents are not able to do. So yes, going back to the now sitting on the table, you ask now to pick up that book. If you have someone doing Wizard of Oz, then of course it's no problem for them to kind of make sure that now orients towards the book and performs the correct actions, even if it can't actually pick it up. But this kind of situated social perception, once you take the human out, it becomes a really big challenge for robotics developers, and it can set these unrealistic expectations that could take years or even decades to deliver. So yeah, it's something that I think, especially with physicality, we have to think about so much more. Now that robots are having much better language capabilities, and indeed, many in the first, and from probably 2005 until 2020, a lot of the Wizard of Oz engagement with social robotics research was doing language, and now language is becoming far more autonomous, but the physicality still remains a really big challenge. So moving to the fourth challenge, and this is that context matters. And again, when looking at that Tesla bot example, I think that's really interesting. And it's not just Tesla. There's, you know, Amazon. There are other developers that are really aiming to develop these kind of one-size-fits-all, all-purpose humanoids. And why do we have to think about context? Well, we have to think about context because when we think about humans, we all have human bodies, and with these bodies, we can do many different things and many different contexts. Our bodies might, and the way we dress, the way we look, they might signal medical authority and competence, they might signal athleticism and entertainment, or perhaps guidance and patience, depending on what context we're in, what our behaviors are, where we're placed in. But it turns out, with some work that I've done with one of my PhD students and colleagues at University of Glasgow, people don't really see robots in this way, and they do not really think that either from a developmental perspective, so we've had people kind of come up with their own designs for what robots they'd like to see in different contexts, and we've also shown people a bunch of different robots designs and asked them to kind of place them into contexts. And what we find in this work is that there's not a one-size-fits-all robot design. So some of the examples that people came up with for healthcare robot designs, we gave them a little kind of paper doll toolkit to kind of design their own robots. We also let them draw whatever they wanted on top of that. We see healthcare robot designs that look like this, entertainment robot designs that look rather different, telepresence robot designs that look different again, and education robot designs that look different too. So we don't see a lot of overlap between these contexts when we ask people to either design robots that might be good in these contexts, or when we ask people to look at a bunch of robot designs and say, which context would you assign this robot to? So unlike the human body, what this means is that robot bodies are just not as adaptable across the many different contexts and requirements that we have great hopes of having social robots deployed in. And we've done a bit of work as well about cross-cultural expectations. And this is something that is super interesting because we sometimes have tunnel vision with the populations we're working with or the contexts in which we're working. Of, this is what people want, the people that are around me, they're in my kind of cultural context. But when you get into really quite diverse cultural contexts, these wants, these expectations can really start to change. And also when we think about different communication styles. So what this means is that we have a little bit of an embodiment design problem, and it's likely going to be impossible to design one body capable of satisfying multiple contextual demands. And again, you might come back to what these companies like Tesla, like Amazon are doing with these, like Boston Dynamics, that have these kind of humanoid robots saying like, oh, well, once we have these, then we'll have robots to do all these things. But can you imagine Atlas standing up in front of a class? Like, it's not, we see for the education ones, these like very friendly faces here. And yeah, it's going to be tricky, I think, to have something that is a one size fits all. And that's not a problem. We just have to be aware of it. So the fifth challenge I'd like to really focus on, and this is one where I think work from those of us who are working in brain and behavioral sciences and kind of human psychology have a lot to add to this, is what goes on when embodiment interacts with human psychology and what these interactions might tell us and how we might want to think about them. So if I show you this picture here, who's seen Austin Powers, the original Austin Powers? A few people, not many. I date myself here with how old I am, but that's okay. So if you've not seen it before, you'll probably think that I'm showing you a picture here of who is presumably Austin Powers, surrounded by scantily clad women, and that's pretty tasteless in this day and age to have a picture like this up there. And yes, that might be tasteless, but if you've seen the film, you'll know that that's not a bunch of scantily clad women surrounding the hero of the film. They're actually robots with deadly weapons hidden in strategic places. So if you were to approach these agents with that knowledge, you would behave and expect things really differently than if you just had what you saw on the surface. And that's a really important thing that I think developers and engineers aren't always thinking about in the social space, which is, okay, what's the human bringing to the human side? What's the human side of human-robot interaction? What are we bringing with our own baggage, our own expectations, our own experiences, our own fears to an encounter? So we've done a little bit of research on this, again, deploying both behavioral and brain imaging measures together, and we didn't use Austin Powers stimuli. Instead, we use these very boring, ancient poser stimuli here. I don't know why some are repeating and some aren't, but that show a human agent or a kind of weird humanoid robotic agent performing really simple tasks. So we had about 10 different tasks like this. So some were throwing a ball up in the air. Another one was putting pens into a cup, stacking blocks, wiping a table, a bunch of really simple bimanual actions. And we not only showed people a bunch of videos that had either this human form or this robot form, but we also gave them a bit of a cover story. And we told them while they were having their brain scanned that, okay, the next 10 videos you're going to watch have been made with this really sophisticated human motion capture technology, and kind of gave them pictures of what that looks like. Or the next 10 videos you're about to watch were made with computer keyframe animation. And we didn't just tell them these kind of little things just have a little screen up before they watched a bunch of these simple bimanual action videos. But before they even got into the brain scanner, we had them watch a half-hour documentary, which we made. But this is with Max Planck Institute resources, so it was very professional, where we told them the history of how these types of animation techniques work. So we had a lot of footage from Avatar, from Polar Express, from many of the different films where at the time motion capture technology with human bodies and stunt, also Lord of the Rings, and stunt actors in these suits were making really sophisticated artificial agents. And of course, in this documentary, we also explained computer keyframe animation. Now, these studies were run, more than 10 years ago. So people's kind of understanding of these things were less than they are now anyways. And also these kind of technologies were, of course, less sophisticated then than they are now. But the really important thing from a psychological perspective is in this documentary, we spent a lot of time with the human motion capture talking about the human is at the core here. And for the computer keyframe animation, we spent a lot of time kind of showing how this is all just, the magic of algorithms. There's no, people press a button and then it just goes and there's no human involvement whatsoever. So in this way, we have what's really a powerful design for doing brain imaging studies, because we have what an agent looks like. So it either looks human-like or it looks like this robot, and what people believe about it. So either this agent's actions come from humans in motion capture, or they come from kind of human out of the loop computer algorithms. And in this way, we can start to pull apart what the kind of influence is of looks and knowledge. We also told people that this study was funded by the German Film Commission, and they wanted to know which animation technique was more effective and kind of like engaging people's brains, but also their perceptions of smoothness and aesthetics. So it was a multi-layered study. And we found a lot of things we've done a few studies with this now, but I'll be showing some of the data from the 2016 study here. We found a bunch of different things, but the most interesting ones are that behaviorally, when we ask people to kind of rate these videos on how smooth they are or how pleasant they are to watch, we don't see any difference at all whether they're watching the human avatar or the robot avatar. But when people are told that these videos have a motion capture origin, people like them and they rate them as much more smooth and pleasant to watch compared to when we tell them they have an algorithmic origin, even though, of course, the animations are identical. There's no differences between these. So kind of not what they look like, but what you believe is a much more powerful predictor of how effective you find these animations to be. And again, coming back to some of these brain regions that are implicated in mentalizing and thinking about others' minds, our brain data show us as well that it didn't really matter whether these agents looked human-like or looked robotic-like, but if you were watching ones where you believed that they had more human origins, we saw more engagement of these brain regions which are implicated in thinking about others' minds, and these really kind of highly sophisticated mental model making of other social agents. So that was really interesting to see that it's not just about the looks or the kind of the movements of an agent, but like what we believe and what we maybe as robotics developers tell people to believe about agents have really profound impacts on people's ratings, but also their brain engagement with these agents. So this can bring us to the question, how might we want to embody social AI? What is the best way to do it? We can ask the question, should social artificial intelligence be embodied in traditional humanoid robot forms? I hope you'll take away from this talk that the answer is no, it's not always necessary, and sometimes that can work against you because it will set up expectations that might be very hard to deliver upon, and if you fail to meet those expectations, you will lose people as potential interactants, customers, whatever you're looking for with those robots. So I think we're really at this golden place right now. There's a really good opportunity for rethinking embodiment that serves a social function rather than relying on mimicking the human form. And again, we can go back to thinking about Paro. Paro is not up here. These are some more recent robots, which again, some of you might be familiar with, but you'll see that they're all a far cry from the kind of more traditional humanoids that have struggled and have not done well. Does that mean that these ones will succeed? Definitely not necessarily, but there's a chance. There's something different that we're thinking about here. So I'd like to conclude with a slide where we can talk about some of the enduring challenges of social embodiment. And what I hope you can take away from this talk is that bodies and forms of robots can make promises, and if a robot's embodiment cannot uphold these promises, human disappointment and robotic failure and probably ultimate company collapse will ensue. And again, I'm really focusing on the social sphere here, not in physical robotics more broadly construed. So what this might mean for engineers is that if you want to develop embodied social agents, deeper collaborations with psychologists from the design phase onwards can help to perhaps better understand the human impacts of physical embodiment, and which psychological levers are the most effective ones to pull in order to maximize people's social engagement with these machines. And for the industry, for those funding and looking to really supercharge the development of social AI that's embodied, really recognizing embodiment not just as a technological challenge, but as a psychological challenge as well. So if we think about how people socially engage with these machines, not just what they look like or what they can do, or just kind of part of this whole picture, we're not going to really be able to be aware of the assumptions that people might bring to socially embodied AI until we try to excavate those assumptions and really see what's going on. So I hope you've learned something new here. I hope having a neuroscientist and a social roboticist in this crowd has not been too foreign. And I'll just put a little plug. This was the original title of the talk. And again, the slides today come from a piece of this very long paper. And it's out in January, but it's available right now too. And I'm really happy to hear your thoughts and answer any questions. So thank you.